All right, so welcome back. We were here, computational complexity, awesome stuff. And so we were on this slide. We talked about what big O really means according to math, and we discovered why these fancy rules make it so that we can say 5n, or sorry, make it so that we can just say n instead of 4n plus 3. Okay, because we can use that constant, set it to 5, and then find some k for which the graph of 5n dominates 4n plus 3. Okay, that's the idea. So we talked about big O, and we also noticed that big O just means upper bound. Okay, so technically 4n plus 3 is big O of n squared, it's big O of 2 to the n. Usually we should say n. We want the tightest upper bound though. Okay, and so I'll talk about big theta, because that's essentially what we mean when we say big O these days. So some terminology. Go to this website, it's super fun. They have this chart. Let's go there. Know thy complexities. So there's this fun chart, and it shows you all the different things. You have constant time, logarithmic time. Those are all excellent, they say. I'll make this bigger. Excellent. Linear time, it's all right. N log n, not horrible. Horrible, though, is exponential. Sorry, horrible, though, to them, apparently, is not exponential, but polynomial. So n to the power of a constant is polynomial time, we call it. And log n we call linearitmic time, and we'll talk about that with sorting. We all know these three already. So polynomial time, then exponential time is a constant to an n. Okay, so that's that. I would say n squared is not always horrible, but definitely exponential is always horrible. And then n factorial, that's always bigger than 2 to the n, because it's like n times n minus 1 times n minus 2, where this is just times 2 all the time. And factorial ends in 2. It starts in a much higher number. Okay, so that's the idea. You should never be writing algorithms that are exponential or factorial unless you know that there's no better way. And there are some for which there is no better way. And this website's also nice because it has other fun stuff, like all these things we've talked about. Arrays is the worst case for searching an array O of n. Oh man, we know this already. All the stuff that we're going to learn in this class, sorting things by the poster, why not? But yeah, that's where I want to leave us there. Now let's talk about other things. So we talked about big O. Let's talk about big omega. Now, big omega is essentially the opposite of big O. It means that you found a lower bound instead of an upper bound. Okay, so let us do this. Here I have n squared and 2n plus 20. So let us say that, let's pretend that this was really 2n, and this can be our g of n, and this can be our f of n this time. They've swapped. So honestly, we can go even further, and we should say that this is, let's just call it n. And maybe we could make this n squared different. It'd be like 2n squared plus 7, something like that. So we can say that f is big omega of g. So 2n squared plus 7 is big omega of just n, because n is a lower bound. Okay, so that's essentially it. Again, you can find those constants, like maybe you have to find the first spot where it's true that it's always smaller. Okay? So from then on, that's our k. From then on, we can pick a constant to multiply by ourselves. We don't even need one this time, apparently. That will always make us less than the thing that we think we are a lower bound of. That's big omega. I'm not really going to ask you about big omega. I might ask you about lower bounds, though, but this is just what people mean. When you get into upper division computer science, then this starts becoming necessary to talk about. Okay. Big theta, though, is very important. So I'm going to write this right here, and this is what I want you to remember for the rest of your life. When we say big O in computer science, we mean big theta. Copy that. Copy just the text, please. Okay? Ingrain this in your mind, because big O, mathematically, means this madness, where you could totally say 2 to the n for 4n plus 3. Big theta is a tight bound, okay? Big theta is this. So in this graph, we're saying that f is big theta of g, and that's because we can bound f on 2 sides by g, depending on which constant we pick, okay? We can make g an upper bound and a lower bound, depending on a constant, okay? That is the idea. So we can pick a constant c1 and pick a constant c2 that will be at the lower end a lower bound. So the same function can function as a lower bound and an upper bound. So it's very tight, we say, okay? They're very close. And in English, whenever you say big theta, we're saying that f and g grow at the same rate. And it's the tightest bound, okay? So everybody always means big theta when they say big O. All right? That's all I want you to remember. And so for example, let me give you an example of this. So this is why we can say 4n plus 3 is big theta of n, because I can choose constants. I can choose 5. Let's see, yeah. I can choose 5n. That'll be the upper bound as the upper bound. And I can choose 3n as the lower bound. And I can pick, those are my 2 constants, c1 and c2, and I can also pick k, where I want to start this process where this will always be true, where this will always be a lower bound and an upper bound. It's not true at 0, but maybe if I pick my k equals to 100, then this is equal to 403, this is equal to 500, this is equal to 300, and so from then on out, this is smack dab in the middle of 2 constants times just n. Okay? So if that made sense, you are golden. So this is 4n plus 3 is big theta of n, and technically, when I drew that, I drew it as a lowercase theta. It's that. That is capital theta. All right? That's all it means. The tightest possible bound, bounded above and below by the same function. Okay? That is big theta. And so notice we can't say that. We can't say that 4n plus 3 is big theta of n squared, because that will always eventually start dominating. Okay? And that is the beauty of it. It forces us to use the tightest possible bound. Otherwise, the math just doesn't work. Okay, so that's big theta. I love it. Always use it. You might be wondering, just for your own knowledge, why these are all Greek letters. Big theta, big omega, big theta, and why we use just O. And let me tell you that O is not actually O here. It is the Greek capital Omicron. I think that's how you pronounce that. Just like how the Greek capital Eta is, it looks like a capital H. So it's really a Greek letter. We just say O instead. Okay? And then finally for all this, I just want to drive the point home that constant doesn't necessarily mean fast. I can make a function, or I can make a for loop. I is less than 10 million. I plus plus C out I or something. This is 10 million steps, constant time. Okay, so just be wary of that. Normally it means fast, but it doesn't have to. Okay, it just means that you can count and it will never change the number of steps. Okay? Constant does not necessarily mean fast, which is funny. Okay, now finally, we've talked about math enough. Let's talk about actually timing our programs. People profile their programs and try and figure out how fast they are, and our programs are not very good at counting their steps, but they can keep time pretty well. Like, here's my clock. It's always normally correct. So here's some stuff that you'll be using in your lab. I'm going to make you write a little timer for some things. Okay, I'm going to make you write a timer class. And so all this stuff lives in the ctime header. And this should also be bold. That bothers me. And we can also make this constant bold, because why not? Alright, so this lives in ctime. And it will let you figure out how long an amount of computation takes. So this is the start time. You call this clock function, and it stores the start time. And then you'll call it again once you're done with the stuff you wanted to time. And then you'll store the end time. And then the seconds in between, this header gives you this clocks per second constant. And you can divide by that when you subtract start from end, and that will give you time elapsed in seconds. So you're going to write a class that does this in your lab this week. Okay, so I've made a sample program for you, and here it is. Here's what's going on, and I think I want to change it up a little bit. Let's just like keep track of a sum or something. Something simple like that. And so I'm just doing everything that I pasted in there. So start the timer, run my long function, stop the timer, and then calculate the time elapsed. And something that I was doing wrong was I forgot the static cast double, and that's because n minus start is probably going to be an integer kind of value, and so is clocks per second. You need to make one of those a double so that it's actually a double division happening. Okay, so that's essentially all I needed to say there, and let's get this compiling and get this running for you. So it's actually really quick at doing that summation. How can we make it longer? I think I know. Long everything. This can get bigger now. Let's add another 0. No? How about another? It technically took longer. Another 0? Yeah, there we go. That one almost took a second. I think if we add one extra 0, then it'll actually take like 10 seconds. So it's very quick to do things in your computer, as you can tell. So depending on how many gigahertz your processor is, that's 100, 1,000, millions. Yeah, so just a couple billion things. And if you have a 2 gigahertz processor, for example, it's 8 seconds. Or 6 seconds, I don't know. Something like that. So that is timing things, and of course I'll give this file to you. Okay, moving on to a recursion review. Let me confirm that I'm actually recording right now. Yes. Yeah, let's talk about recursion for just a second. If you've never seen it before, we're going to use it a lot in this class, and then also we need to figure out how recursive functions are like measured in terms of time and space complexity. We've only talked about time complexity so far, so we'll get to that in a second as well. So recursion, it's just when you have a problem and you find that problem inside of itself. Maybe you've seen those like stacking dolls where you got one and inside of the other is that one, then inside of that one is that one, and then just go on forever. Those it starts with an M. I don't exactly know how to pronounce it, like Matryoshka or something like that. Those dolls. That's essentially recursion. You find the same thing inside of yourself. Okay. So recursion for programming is you're writing a function and it's calling itself, usually like explicitly. You might have to go through a few function calls to call itself again, but normally in this class, your functions that you write are just going to call themselves. Okay, and that's what recursion is. So the key idea is when you make a recursive call, when you call that same function with the same name, it must be on a smaller argument. And you have to define what smaller means because it changes depending on the problem. But the reason it needs to be smaller is so that you eventually hit your base case and your computation completes. It eventually stops. Okay? And so a base case in recursion is when you have an input and you know exactly how to solve it without doing any extra work. Like you found the smallest doll, you know the answer for that one. Okay? And then the recursive case is, of course, what makes it recursion. It's when you can break down the input, you can find a smaller version of the same problem inside of itself, and you can break down the input, call the function recursively, and what that'll do is eventually it'll hit the base case and then build itself back up from the result of that recursive call that was on something smaller. Okay? And the mathematical reason why it works, if you care at all, is this. I'm actually just going to make a blank slide. So when we have a recursive problem, let's pretend that our problem is very generic. It's called P, and it takes a certain input. P of n is our problem. Okay? So a recursive problem is one where we can find P inside of itself for smaller values of n. Okay? So a base case looks like P of 0. I can immediately give the answer for P of 0. I don't have to do anything else. The recursive case looks like this. Assuming I had the answer for P of n minus 1, or something along those lines, I can use that result to generate the answer for P of n. Okay? And this is the reason that recursion works. It's because your recursive call is always going to be to a smaller thing, and it's going to go and solve that problem. Eventually it'll hit the base case. And it will use that, so use the solution for that smaller version of the problem to solve the original version of the problem. As long as you do that correctly, you get to assume, you actually get to assume, it's kind of magic, assume this works. You get to. And that's kind of beautiful and magical. As long as you build up the solution correctly, it just automatically works based on that. Because assuming you implemented the base case this way and the recursive case this way, you can solve any problem, because you could start at P of 0 using your base case rule, and then you can just use the recursive case rule as many times as you need to get the next thing. I can use P of n minus 1 to get P of n, enter n equals 1. I can use P of 0 to get P of 1. I can use P of 1 to get P of 2. That's what the recursive case gives us. And so this is kind of like a bottom-up approach, a bottom-up proof as to why this works. And you'll learn about this in CSCI 26. Okay? It's called mathematical induction. All right, so let's talk about 3 examples of recursion, and then I will give a quick example of how to find the complexity of those things. That's not something I'm really caring about in this class. That's more for an algorithms class, but it's good for you to have seen it. So, all right, let's do factorial really quick. So a factorial of a number like n factorial. This is a recursive problem because can you find, because can you find a smaller factorial inside of this factorial? Like pretend it was 4 factorial. That's supposed to be 4 times 3 times 2 times 1. Where's the smaller factorial? Oh man, it's right there. There's 3 factorial. So n factorial just so happens to be, in the recursive case, n times n minus 1 factorial. Okay? And then the base case is 0 factorial is defined to be 1. You could also start at 1. Okay, so that's essentially the recursive process for this. And I hope you see it, how we can break it down. This should hopefully be a review. So I'll do recursion examples. So I'll make my function called fact. It returns an integer and it takes an integer. I guess we're calling it n. And if, in the base case, n is 0, we return 1. Otherwise, we return n times factorial of n minus 1. Okay, so we made a recursive call solve the smaller version, or solve a smaller version of the problem, okay? And so long as we build up the correct answer, we get to assume for free that this did the right thing, as long as we build up the correct answer based on that. We get to assume that that returns the factorial of n minus 1, and then it's our job to build up the factorial of n, and we need to just multiply by n to get that. Okay, so that's a correct recursive case. We get to assume that it works. Super cool. And then we'll just run fact3. Oh, let's see here, what have I done wrong? Oh, it's just recursion examples. Sorry. And apparently that's 6. And yeah, that makes sense. Okay. Moving on. Fibonacci. This is actually interesting because it takes 2 recursive calls, if you remember that. So the Fibonacci numbers, the Fibonacci sequence, it starts at, it either starts with 0 and 1 or 1 and 1. Let's start at 0 and 1 for no good reason. So if n is equal to 0, we return 0. If n is equal to 1, we return 1. But after that, it's always the sum of the previous two. So 0 plus 1, that gives me 1. Okay? And 1 plus 1, that gives me 1 plus 1, that gives me 2. 2 plus 1, that gives me 3. Okay? And then so on. 5, 8, 13, on and on forever. That's the Fibonacci sequence. So we actually have 2 base cases. All right, so fib of 0 equals 0. Fib of 1 equals 1. And then we can do recursion because you can see that the value of Fibonacci of this n is whatever the sum of Fibonacci of n minus 1 plus n minus 2 is. Okay? In general, fib of n is fib of n minus 1 plus fib of n minus 2. Okay, so you see how we found the same problem inside of itself. So I'm considering a certain n, and all I need to do is I could solve smaller versions of that problem and add them together and get my answer. All right? Oh, and sorry, this is 0 here. Alright, that's fact 3, see out fib n, fib, I don't know, 5. And so this is all going to work just fine. And it's going to give us back 5. And the reason it's going to do that is, let's see, am I going to have time? I think I will. The reason it's going to do that is because here when I call it from main, this is what's happening. If you've never seen this before, it's super helpful. Main calls fib, oh gosh, I think I'd rather do this for factorial. Let me show you how factorial works. So fact of 4 will call fact of 3, just right there, because we need to wait on this answer before we can multiply our n by it. Fact of 4 calls fact of 3 because it's waiting for that answer. It needs to make a recursive call. And fact of 3 calls fact of 2. This is our call stack. And fact of 2 calls fact of 1. And these are all waiting on the smaller factorial call because they needed to multiply their n by that value. Okay, so now fact of 0 hits the base case and it returns 1 to its caller. Gives back 1, and then fact of 1 can finally take that answer and multiply it by its n, which happened to be 1, of course. So it'll return 1 times 1, okay? Which will return 1, or 1 times 1, I guess. And then fact of 2, who is waiting for fact of 1, who was itself waiting, everything's all completing, it's unwinding now. That has an answer, it was 1, and now it can multiply its 2 by that. So we get 2 times 1, which is 2. Then fact of 3 was waiting for fact of 2, and now it can multiply its n by it. So it gets 6. Okay, and then fact of 4 was waiting for fact of 3, and now it can multiply its n by that recursive result of fact of 3, and so it can give back 6, 12, 18, 24. Okay, that is the idea. Isn't that fun? And that's why recursion works. And of course, all these things are going to pop themselves off the stack once they're done, but that is why it's working. And then Fibonacci, it's a bit harder because there's 2 recursive calls, but it's essentially the same thing. And then finally, let's see here. Let's sum the values in an array. And this is a bit different. So let's pretend I had my array. Here it is. ARR. I don't know, index 0, 1, 2, 3, 4. Maybe it held 1, 2, 3, 4, and 5. And I wanted to sum this. Can you find me this problem inside of itself? So inside of this array, can you find me a smaller array to sum? And I think you can. You can choose, here's a smaller array, 1 smaller. Here's a smaller array, 1 smaller. I mean, you can find a bunch of smaller arrays, but how are they going to help you, I guess, is the question. It's usually we break it down into our current element and then the rest. Okay, so it's like our current and then a smaller array. And remember that every array is just a pointer to its first value. So technically, if I had ARR of 1, 2, and 3, and this started at like address 100 or something, ARR is really a pointer. When we say it alone, it's a pointer to the first thing, it's 100. So that represents this whole array. So if I wanted to represent the smaller array, everything after it, I can just give the next address, okay? I can say, I don't have to say +4 when it's ints, I can just say array +1 actually. Dun dun dun, and that will give the next spot. C++ is smart enough to know that +1 just means the next index, the next possible int you could point to if it's ints. Okay, so that gives me 104 there. And so technically, this is the smaller array. And so that's how I can make my recursive call. If that makes any sense at all, which it doesn't have to. This is just getting your feet wet before we talk about linked lists, because it's going to be very similar. So we have int star array, dun dun dun, and then int size. And so, remember that every array is a pointer to the first value in it. To get the sum of an array, I can do the following. I can add my current index, array 0, and then I can add the sum of the smaller array. And that will build up correctly the answer for the sum of the biggest array, this whole thing. Okay? So if size is 0, obviously the sum is nothing, because that's an empty array. Sum of empty array equals 0. Else size is not 0. I will return array of 0, so my first element plus the sum of ARR plus 1, size minus 1. So this is a bit fancy. Don't worry, it's called pointer arithmetic. I don't think I'll ever ask you to remember it. But what it's doing, if you care, is it's making the smaller array. It's finding a pointer to the start of a smaller array, 1 past our current one. So it's going to give back this array right here, plus 1. That's what that means. And then the size, we'll just keep track of how many elements are in it. So eventually it'll get down to 0. Okay, that's what sum array means. And so that's a recursive algorithm. To sum those things. Okay. Yell at me during office hours about this if you are interested. I'd be happy to explain more. I love recursion. But let's get into complexity now of recursive functions. So we need to talk about recursion trees, and I know you read about this in your book, so we'll go through it quickly. It's not a whole lot to say, and this is a more advanced topic, I think, so we don't have to care as much about it here in this class. So what you do is you create a tree that shows how many recursive calls are being made for a certain size input. And you can also figure out, and that'll show you like how wide the tree is. And then you need to then figure out, to sum them all together, the height as well. Okay, so you need like the width and the height, W and H. So how do we do that? Let's give an example. So what's the complexity of the following function, Fibonacci? All right, so here's our function, and for this one I'm just starting it at 1, 1. So 1, 1, 2, 3. I could have done 0, 1 as well, but this is simpler to write. Okay, it's just the first two values are 1 in this case. Okay. So this is alternate Fibonacci, and what it's doing is, let's say we're calling Fibonacci of, I gotta be careful here, Fibonacci of 4. What it's going to do, because it's not the base case, it's going to call Fibonacci of 3 and plus Fibonacci of 2. And then this one's not the base case, it'll call Fibonacci of 2 plus Fibonacci of 1, and this one will call Fibonacci of 1 plus Fibonacci of 0. So this is a base case, this is a base case, this is a base case, this is not yet. Fibonacci of, so Fibonacci of 2 will itself call, because it's not the base case, Fibonacci of 1 plus Fibonacci of 0, and so now I have a bunch of base cases. So notice, though, all the repetition. Okay? That's what makes this quite horrible. I'm repeating all these base cases, and I'm repeating fib 2 here, fib 2 there. And if this was like fib 5, here I'd have fib 3, and I'd repeat all of this right over there. You see that? Be like, boop. And so suddenly, all of these base cases are happening so super often. Okay? So, in essence, the way we can model this is the height of this tree is essentially 1, 2, 3, 4. So it's got 5 things in it. 1, 2, 3, 4, 5 things. And each time, at each level, oh man, how many things are there? So at this level, there's 1 thing. At this level, there's 2 things. At this level, there's 3 things. At this level, there's 4 things. It'll be over here. It's all being, and then here you can see there's going to be 4 here and 4 over here if we generalize. So now there's 8 and there's 16. It's all doubling. Oh no, oh no. So that's kind of what I want you to see here. And so do some math. The upper bound of calls to fib is 2 to the something, all of these things. 2 to the 1, 2 to the 0, plus 2 to the 1, plus 2 to the 2, plus 2 to the 3, all the way to plus 2 to the n. There should be a dot 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 in between. And that just so happens to equal 2 to the n plus 1 minus 1. And if you know binary, that's why. It's like dun 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 plus 1 in binary is, let's see here. Yeah, plus 1 in binary is all of this stuff. Okay, that's all. It's essentially almost all of this, but we want to know how much this is, so we just subtract 1. So it's super simple. So that's why it's that. And yeah, so each time we make a function call, we're doing constant work. It's just testing things, summing things. But the second we make recursive calls, that's when we double the work. Okay, so 2 to the n work total, because it's 2 to the n function calls times constant work. So it's of 1 work times of 2 to the n function calls. And it's not actually that, because this tree is not always that deep, but we're kind of pretending that it is. See how this level only has that, and then this level has two things. It's kind of leaning this way, if you can see that. But we don't have to care. We're looking for an upper bound. Okay, so it's a little bit less. It's really like the golden ratio, so like 1.5 something to the n. It's still exponential. Okay, so let me try and run fib of 200. Let me show you an exponential algorithm in the wild. I'll just wait here, get a sip of water. We'll be done soon, right? Well, I'm just going to kill this because the answer is no. So here is the Summit supercomputer, which is in Tennessee. It's the world's fastest supercomputer at the moment. I had to look this up. It has changed. So it is capable of doing 2 × 10 to the 17 operations per second. So Summit, very fast. It is the peak. It's like a mountain, obviously. Well, assuming that one fib function call takes one operation, which is really stretching it because it's doing a bunch of little tiny steps. So it's not technically true, but assuming that that was true, well, that divided by that many operations per second, divided by 60 minutes per second, divided by 60 minutes per hour, divided by 24 hours per day, divided by that many days per year, equals 3 × 10 to the 175 years. That's how long it would take to complete fib of 200 on this supercomputer. Okay? And just to give you something you can compare against, that's several times more than the age of our universe. But we can make an iterative version, can't we? We know how to do that. Dun dun dun. I'll probably get an off by 1 error, but you know what I'm trying to do. 0, that's 1. Otherwise, we're going to loop. 0, or no, that's 1. Something like this, and then we loop for like n-2 times. Again, I'm probably gonna have an off by 1 error, but you know what I'm trying to do here. And this is -2. Okay. Dun dun dun. Equals n-1 plus n-2, something like that, and then we need to make the old n-2 now be what the old n-1 was. Oops. And then we'll return n-1, I think. So let's see. So I know 0 and 1 will work. Let's try 2. Let's see if I'm doing that right. 1, 3 should be 2. It is not quite. About 4. That's 2. 1, 1, 2. So it's 1 off. I should do this loop one more time then. So now I should get fib iterative of, I guess, 0, 1, then 2 is 1, 2 should be 1, and then 3 should be 2, and that'll be correct. There we go. All right, so fib iterative of 200. That's super fast and actually doesn't fit inside of an int. So maybe we could use long longs if we really wanted to, but you get the idea. That, the iterative version, take a second to think how long that takes. And then let's go back to the code. This is the 0 case constant, in the 1 case constant. In the non-0 and non-1 case, we're doing a loop that takes constant time in the middle. So this is constant work here. And we're doing that constant work on the order of n times, n minus 1 times. So it's essentially going to be an O of n algorithm. Okay? And so now you can see the difference, the huge, huge difference between O of n and O of 2 to the n. Yeah? Huge, huge difference. And that brings us to space complexity. So we've so far focused on running time complexity, but that's because people more often care about that. We have a lot of RAM on our machines these days. And then also, everything that we've talked about corresponds very well. It all just carries over. So it's not a huge deal. So space complexity is going to be all the obvious things now that we know how to say big O of anything. It'll just be, it's the amount of space used to store stuff inside of an algorithm. So for example, if I wanted to reverse an array, I had an array ARR, that needs to exist ahead of time, right? I had 1, 2, 3, and I want to turn this into 3, 2, 1. So if I do it in place, if you know the algorithm, you like start at both ends and you keep swapping towards the middle. That requires 2 different indices that you keep on manipulating, and you're just essentially doing a loop that takes half the length of the array. So that's going to be O of n. It's O of n time complexity, but it's constant space complexity. Because you assume you already had the array. I mean, that's not extra. You assume you had that. It just takes 2 extra variables or so. Maybe the iteration variable also counts, so maybe 3. Okay, so not a whole lot of extra space, and we can count that number, so it's O of 1. Constant space. If, however, your function makes a brand new array and returns that, it does not touch the original one like the in-place one does, then we have issues, okay? So this involves now, it's got to make a new array, okay? And that array is of size n. And it also might need to store some extra variables to help it like iterate through that thing. It's got to store I, and it's got to make I start from n and like start adding into a certain index. So maybe you need some extra variables as well, but you need to make a size n array. So you're going to need n more space plus, I don't know, some constants, okay? And so that becomes O of n space complexity. Okay, so this is linear space because you're copying the array. Perhaps you wanted to double that array. That would be 2 to the n space, like you're doing in the vectors, okay? So now this all makes sense, I hope. But still, in the vector case, that 2 goes away again, and you know how to do this. Okay? So another thing is that you need to think about the stack when you're thinking about the space complexity of a recursive function, because it's calling itself, and it's implicitly storing information there. If we go back to the factorial example, notice that the factorial example inside of the function itself, it's only storing in n, okay, and maybe the result of like a multiplication. So it only has 1 variable inside of it, so it's constant space inside of this function, but how many functions are being called at once? At most n. You see that? In the worst case, we're at the base case, and we're waiting on the original call down in the base case, and so we need to store n plus 1 function calls, okay? Calls to fact on the stack. At the same time. So maybe each function itself took constant space, but in total, in the worst case, they're going to take linear space. You see that? And of course that blows up again for Fibonacci. Not as much though. You're ever only in one function at a time, but it's going to do the same kind of thing. Actually, I think it'll also be linear space. But that is the idea. You have to consider the stack itself, the function call stack, because that is implicit inside of a recursive function. So Fibonacci, it's only ever going to be calling a certain function at a time. Maybe fib5 calls fib4, then it's working on fib3, which works on fib2, which works on fib1. These are all waiting on each other. So the stack is only ever going to be 5 high. So again, it's linear space. Okay, so hopefully that's making some sense. Space complexity is something that we'll consider some more later, I think. But time complexity is something that I really want you to get in your head right now. And I think that I have covered that so far. So with that, I think we're done with these slides. Now I have some examples or some exercises for you. Please complete these if you'd like. Yell at me in office hours if you have any questions. But try and write some functions with certain time complexities. I think n cubed will be easy for you. But how about n cubed log n? How can you do that? Okay, somehow you need to like multiply the fact that maybe you can do some loop iterations, but inside of the innermost loop, maybe you can do a logarithmic thing, something like that. Okay, try and figure out how you might make a function that has this kind of time complexity. Okay, and that would be really helpful for you, I think. Same over here. Let's see here. Write a recursive function to print out an array in order. So that's very similar to our sum function. Get that working. You can copy what I've done in the starter code, or not in the starter code, but in today's code. That sum array function, and figure out the complexity, both space and time. I don't think you're copying the array, so it shouldn't be that bad, right? Well, you'll figure that out, and then try and draw the stack diagram for this function that you write on a certain array. So 1, 2, 3, try that. Because for main, for example, maybe you're going to call print on 1, 2, 3, or essentially a pointer to the first element, right? And then maybe you'll break it down, you'll call print of 2, 3, something like that, right? And so figure out how tall that is, what order it is, and maybe what I've written here is not right. Take a look at all that. And then finally, I just want to talk about the midterm, because assuming you're watching this during the correct week, there is going to be a midterm during week 6. Okay, and so this is right now week 4, assuming you're watching this in the correct week. So, how are we going to do this? Let me go to Canvas. Oh, and also, CTime, you can always look that up and see what the clock function does, what clocks per second is, and you can see some extra examples. It's essentially what I showed you. Okay, so that's that. And so, I'm going to be releasing this page this week. Obviously, I haven't made it yet, but it's going to be this module. It's going to be called Midterm 1, and I think the way that your Canvas works is it'll just become visible below week 4. When I make week 4 visible, then I make midterm 1 visible. If these ones aren't visible, it'll just immediately show you midterm 1 after week 4. I think that's what's going to happen. So here is information about the midterm. All right, so as for logistics, it will be on Canvas, of course, and it will be available at 12:30 p.m. on September 17th. So that's a Thursday. There it is, it's a Thursday. And then it'll be available until 5:30 p.m. the next day on the 18th, the Friday. So you will hit 4 of my office hours within this time range, and hopefully you can take it during those, one of those. So that's the idea. You can start at any time within that window. It's over a 24-hour window. But this is the caveat. You have to take it during a normal amount of class time. So once you click start, have your water bottle ready, have your computer ready to go. It'll start counting down an hour and 15 minutes. Okay? So make sure to start before 4:15 on the 18th if you're going to take it then. Yeah. And then this is going to essentially take place of our lab. So I'm going to mess around with the due dates for some of the labs. Okay? No, I don't want to be horrible and make you do a lab that same week or something like that. I'll figure out the due date schedule. So don't worry about that. And yeah, the topics is probably what you care about the most. So here is what it's going to be about. The lectures up into week 5. So next week we're going to be talking about lists, and those are going to be the last potential topic to appear on the midterm. Okay, so not any other week 5 stuff like stacks onward. No, just the last part about lists that's due before the midterm. All right, that's all. Oops. And then the rest. The rest of the midterm, or other things that will be on the midterm, are stuff from your Zybook readings, up to and including that stuff on lists. So I'll focus on lists and complexity analysis because there's no chapters on like the big 3 or anything like that. And then also labs 0 through 3, because those will be the ones that have been due before your midterm. Okay, that's essentially my my plan for topics. So just study hard on all those things, and you should do just fine. So it's going to be open book and open notes, of course. I can't like watch your screen or anything like that. But it's definitely not open chat app, so don't be like on Discord or Facebook Messenger or Instagram and like share your answers with anybody. You don't want to feel my wrath. All right, so that's that. And then the final thing is the format, in case you're interested. I'll take some multiple choice questions from the textbook chapters. So the Zybook has some of those, and I'll take a few of those, maybe like 20 or so, and those should be pretty quick. And then after that, the other part of the exam will just be a free-for-all, fill in the blank or coding questions taken from all of the topics up here. Okay, so that's the idea, and yeah, you should do just fine, I think. Now, one thing that you're going to be doing in those fill-in-the-blank questions is sometimes writing a good deal of code. Okay, so I want you to prepare yourself to put code in a Canvas submission text box. All right, so practice copying from whatever editor you're using. Figure out how to copy into your clipboard in Vim, or use Visual Studio Code, whatever you need to do. But remember that there's a time limit this time, so you got to be ready. You got to be ready to copy and paste. You can even write within Canvas, but that might not be very easy because it doesn't like do syntax highlighting or things like that. So that's the midterm. And then to help you study, I am going to give an extra credit opportunity. Okay? So that is this one. And there are a lot of rules, and I should have stolen my slides from CSCI 40 because it's essentially the same. Let me do that very quickly. Here. Dun dun dun. CSCI 40, lectures. Don't mind me, sorry about this. I should have done this before. I think it's during their loops. It's all the same information, but I should have done that. Boop. That's better. Alright, so you have 2 options when you're doing this. So you can create questions for your peers. So it's going to be a discussion. So you're going to reply down here. Be like, hey, I'm writing a question to be on the study guide. I'm making up my own question. And to get credit, it has to be 400 words. And that includes code, so that's okay. So write a nice question. It shouldn't be super easy. You can write multiple ones if that doesn't, if your first one isn't 400 words long. Okay? So it's got to be 400 words. And what you'll do is you'll post your answer 3 days later. You'll give your peers the opportunity to answer the question in detail, and you'll just post a quick answer 3 days later. And yeah, there's an option too that involves answering a question. You can't do that for your own question. Okay? You're required to post the answer. And so that will be 1% extra credit. Okay? And the total, you can do as many as many of these up to a maximum of 2% extra credit. Okay, so you can make 2 questions if you'd like, or your option 2 is you can answer somebody else's question. So you can click reply, and that should be 250 words, including code, and each answer will be 0.5% for extra credit. All right, so that's the idea. Read the rules. Don't re-answer a question if it's already been answered, and you're not going to add anything to the discussion. I don't want just a copied and pasted answer of something that's already on there. So you're essentially making a study guide for yourselves, and maybe if you make some good questions, I'll use them. So that's the idea. I think that is everything that I wanted to say there. Yeah, so that will help you study. So invent some questions that are based on the topics, or answer them. And you can do any combination of these. You can write 2 questions, or answer 4 questions, or some combination of those up to 2% extra credit. And that is about a lab's worth of credit. Okay, so just keep that in mind. Or like 2 homeworks, something like that. And yeah, good luck on everything there. Good luck on studying. And just remember the timeline, when it's going to be. I'll put it in that same place. I'll put it in this midterm 1 place, and so you'll see like midterm 1, click to take the test or something. All right, that's all. Yeah, I think I'm just rambling now. So that's your midterm info, and we just covered computational complexity. So I will see you next week.